When you feel feverish, you grab a thermometer. It gives you a number 101 degree Fahrenheit or 38 degrees centigrade. But have you ever wondered how does this tiny glass tube know how hot you are? What exactly is it measuring? In our previous video, we learned that temperature is a measure of how hot or how cold something is. But hot and cold are very subjective experiences. You probably have a friend who drinks tea as soon as it arrives, while you sit there thinking, how can anyone drink something that hot? The same tea is hot for you, but perfect for your friend. Or think of the winters. One person says weather is pleasant now, while another one bundles up in a sweater and a scarf. So clearly, the sense of hot and cold depends on who is experiencing it. It's subjective. So scientists needed something that would give the same response no matter who was using it, a kind of standard. But how do you measure something you can't even see? Here's the trick scientists use. If we can't measure something directly, we try to measure it indirectly. We simply choose any substance and look for a property that can be measured, like its length, volume, weight, etc. Then we observe if that property changes when the temperature changes. And if it does, we can relate temperature to that property. For example, let's say we take a metal cube and note down its size. Then we heat it for some time. When we measure it again, we find that it has grown slightly in size. So as the temperature increases, the cube expands. Now it's completely up to us how we want to relate the cube's size to its temperature. We could say if its size doubles, its temperature has doubled. Or we could also say if the cube was at a 0 degree temperature when it had its original size, and when it doubled, it is at 100 degree temperature. It is completely up to us. And this way, we just created a temperature scale. But this is our personal way of defining it, and not everyone might agree with it. But that's how one of our temperature scales are created, Celsius scale. Scientists took water as the reference substance and defined a 0 degree when the water freezes and 100 degree when it boils. This way, everyone measures temperature the same way, and everyone agrees on the scale. And this is how most thermometers are created. The most familiar one is the mercury thermometer. When mercury is heated, it expands. So they put the mercury in a narrow glass tube. This tube is so thin that it makes even tiny expansion visible. Then they mark the tube at known points, like the freezing and boiling points of water, and assign numbers to those positions. All the points in between are divided equally, assuming mercury expands evenly with the temperature. To measure the temperature of something, let's say water, you place the bulb of the thermometer in contact with it for some time. If water is hotter than the mercury, some heat flows from the water into the mercury. That's because energy always moves from a higher temperature to a lower one. As mercury gains heat, it expands and rises in the thin tube. The heat transfer stops when both mercury and water reach the same temperature. This state is called thermal equilibrium. Now at that point, the height of the mercury column now shows the temperature of the water. The same thing happens if the water is cooler. Then the mercury in the tube loses some of its heat to the water. Instead of expanding, it contracts and falls in the tube. When both reach thermal equilibrium again, the height of the mercury column gives the temperature of the water. And this is exactly how it measures your temperature when you have a fever. The mercury in the thermometer gains heat from your body, expands, and rises in the column. When it reaches thermal equilibrium with your body, it stops rising, and that's your body temperature. So, mercury thermometers work because mercury expands when heated, and that expansion is easy to see and measure. But mercury isn't the only option. Scientists realized that almost any property that changes with temperature and does so continuously can be used to make a thermometer. For example, the flow of electric current through a metal wire decreases as the wire gets hotter, and this property is used to make digital thermometers. They measure how hard it is for electricity to pass through a tiny metal sensor. That resistance to flow of electricity is then related to the temperature. But these thermometers have some limitations. Mercury thermometers stop working at extreme temperatures because mercury freezes at minus 39 degrees centigrade and boils around 357 degrees centigrade. So it can't measure below or above that range. Resistance thermometers, on the other hand, can go higher, but their readings become slightly less accurate at the extreme temperatures because the change in resistance to flow of electricity doesn't always change perfectly steadily with temperature. Also, another problem was that different materials expand differently when heated. So, two thermometers made of different substances might show different readings for the same temperature. That means their readings depend partly on what they are made of, not purely on the temperature itself. Scientists wanted something more universal, a thermometer that gives the same reading no matter what it's made of. They found that gases are exactly what they were looking for. Experiments show that when gases are very spread out, meaning their particles are far apart, that also means they have low density. They all behave almost the same way when heated. It doesn't matter whether it's helium, hydrogen, or just air. They all follow the same simple pattern. When they are heated, they expand and change their pressure. This relationship is more easily understood by this simple equation. This is known as the ideal gas equation. Here P is the pressure of the gas, V is its volume, N is the amount of gas, T is the temperature, and R is just a constant. Think of it just as a fixed number. Imagine we keep some N amount of gas in a container of volume V. Now when we heat the container, but don't let its volume change, the gas molecules move faster with a higher energy and push harder on the walls. As a result, the pressure rises as the temperature rises. Now look at the equation. It tells us the same thing. When V, N and R are constant or fixed, increasing the temperature increases the pressure. If you are confused, how do we know when we raise the temperature, pressure should also rise? Then let me explain. This is just simple math. Both sides of the equation have to stay balanced. So if the temperature increases on the right side, the pressure must increase on the left side to keep the balance. Simple? Now instead, if we keep the pressure constant, but let the gas expand or contract freely, the increase or decrease in temperature will increase or decrease its volume. So by measuring either pressure or volume, we can directly relate it to the temperature of the gas. These gas thermometers are so accurate and reliable that scientists use them to calibrate and check every other thermometer in the world. So that's how we measure temperature. From a simple mercury thermometer to precise gas thermometers that define our temperature scales. But this story doesn't stop there. Scientists now use sensors. They don't even need to touch the object. Infrared thermometers can read the temperature of things just by detecting the heat they give off. That's how engineers check the temperature of a jet engine or even flowing lava. Then there are pyrometers, used to estimate the temperature in industrial settings, like kilns, furnaces, or molten metal. And for things far beyond our reach, like stars, we use space telescopes that look at the color of the light coming from them. From that light alone, we can tell how hot they are, millions of light years away across space. If you think about it, the idea is the same. Something changes when the temperature changes. Whether it's mercury expanding, resistance increasing, or light shifting in color. Every thermometer is just a clever way of reading what nature is already telling us. And then, of course, there's that moment when someone walks into the room and you think, that's hot. Sorry, that one is purely subjective. No thermometer can measure that. They all break there. If you enjoyed this video and learned something new, let me know in the comments. I would really love to hear your thoughts or your own fun observations about temperature. And if you think someone else might enjoy this little journey into how we measure heat, share it with them too. Also, if you ever feel like supporting the channel, there is a Patreon link below. Don't forget to subscribe so you don't miss the next part, because we are just getting started with the physics. Until next time, stay curious and stay warm.